we'll move on to the fourth and the last part, understanding rocket dynamics using Lagrangian and Hamiltonian mechanics. We'll derive equation of point mass rocket valid in any coordinate system using both Lagrangian and Hamiltonian mechanics, which can be conveniently used in calculation of rocket motion involving complex constraints. Consider a rocket as a point of variable mass moving with velocity v of xi. The differential equation of the rocket motion can be written as mxi double dot into m into x double dot, which is double differential of position vector with respect to time, is equal to the mass of the expelled fuel into the relative velocity with the fuel is expelled plus Fi, which is any force applied excluding the upthrust of the expelled mass. Now adding mxi to both sides, we get this equation where we introduce ui as a new variable, where ui is equal to xi dot plus ci, which is absolute velocity of expelled fuel. We can also express xi in terms of q alpha and t, where q alpha or beta are the generalized coordinates and I is the degree of freedom, where I can be 1, 2, 3, degree of freedom. We can write kinetic energy of the rocket by this equation: half into variable mass at any instant t into xi dot into xi dot, which is equivalent to half mv square. Now dotting this equation with d of xi divided by d of q alpha, we get this equation. And on seeing this equation, we can equate the left hand side equal to this relation can be easily verified, and hence from this we can equate these two relations and we get this final relation, which is the Lagrangian equation for the rocket mechanics, which is this is equal to the derivative of d of t by d of q alpha with respect to time minus d of t by d of q alpha is equal to the mass of the expelled fuel into absolute velocity of the expelled fuel multiplied by partial derivative of xi with respect to q alpha plus any applied force on the rocket into derivative of xi into q with respect to q alpha.